Hello everyone, my name is Afzal and today I will be presenting our project Efficient Spatial Query Processing using R3 indexing, where we implemented using compared branch and bound algorithm for nearest neighbor and skyline search. The goal of the project was to show how spatial indexing, especially R3, significantly improves performance over brute force search when dealing with large dataset. The main objective of the project was to evaluate how advanced index-based search method performed compared to a traditional sequence search approach. We implement both nearest neighbor and skyline search and compared brute force against optimized R-tree-based algorithm. This helped us understand the real-world benefits of spatial indexing and applications like navigation system, ride-hailing services, and property recommendation engines. Spatial datasets are huge and continuously growing. For example, Google Maps, Uber, or food delivery services that uses thousands of search location in real time. Brute force method scans all point, which becomes extremely slow and inefficient and as data increases. To solve this challenge, we need efficient indexing structure like R-tree, which reduce unnecessary computation dramatically. An R-tree is hierarchical data structure that groups nearby objects into minimal bounding rectangles. Instead of checking every point, the algorithm checks region first and only goes inside them if necessary. This helps the system skip irrelevant areas, entirely making spatial queries much faster. The project has two major parts. Task 1 is the nearest neighbor search, which is of three methods, and task 2, which is skyline and has three methods. Each task compared to sequential brute force approach, R-tree-based branch and bound, and third one is divide and conquer with R-tree indexing. Nearest neighbor queries located the closest point to given every location. For example, find the nearest restaurant to me. We generate 200 random query points and compared different algorithms to see which one responds faster. We used facility dataset such as restaurant, shops, and parking lot. The dataset selection followed the student ID based rule. We built a query file of 200 random generated coordinates and measure execution time and accuracy. The first method simply checks the distance to every point and picks the smallest one. This guarantees accuracy, but it's very slow and large due to O(n) time complexity. This method serves as a performance baseline. Branch and bound uses the R-tree to intelligently search only promising area. It computes a minimal possible distance called mindset between the query and each region. If region cannot possibly contain a closer point, we prune it. This drastically reduces the number of checks and speed up search significantly. We constructed the R-tree from scratch by recursively dividing points based on spatial distribution. Each node stores a bounding box covering all points in that region. This hereditary design supports fast pruning during search. Branch and bound begins at the root, maintain the best found distance. For each region, it compares the minimum distance to the best results so far. If the region could not contain a better answer, explore. If not, skip it completely. These techniques avoid unnecessary distance calculating and is the key efficient. The divide and conquer method first split the dataset into two subspaces based on x coordinate. Two separate R-tree bases are built, and we run BAB on both trees of query. The both results from the two trees are selected. Although faster than brute force, this method had extra overhead, making it slightly slower than the standard BAB. We benchmarked all three methods on 200 queries. The result was so far. Sequence scan was the slowest, BAB was the fastest. BAB with divide and conquer faster than brute force but slightly slower than pure BAB. This experimental confirmed that indexing plus pruning dramatically improves query speed. Thank you.
My name is Praveen, and now I'll be talking about task 2 of an assignment, that is skyline search. Task 2 is mainly aimed to identify the skyline from a data set of homes based on two different criteria that are cost and price per square meter. A point is in the skyline if it is not dominated by any other point in the entire data set. The skyline represents the set of all Pareto optimal choices where no single option is strictly better in all dimensions. Now moving on to the next slide, we'll be talking about the core concepts in skylines. In this minimization problem, a point P1 dominates another point P2 if it is better or equal in all dimensions. This means P1 must also strictly be better than P2 in at least one of the measured dimensions. The skyline query's primary function is to filter out all the points in the dataset that are dominated. Moving on to the next slide, we'll be talking about the datasets and the methodologies used to complete task 2. This task utilized one of three city datasets. Those are City1, City2, and City3 TXT files representing different housing markets. Similar to task 1, the specific dataset was selected based on the prescribed formula involving the group's student IDs. The goal was to implement and compare three distinct algorithms for the computing the complete skyline of the selected dataset. And now we'll be talking about the first algorithm used, that is the BNL algorithm. BNL stands for Block Nested Loop Algorithm, which is a sequential method that maintains a running list of skyline candidates. For each point in the dataset, it is compared against every point currently in the candidate skyline list. Points are added and existing candidates are removed based on the dominance check, resulting in the process with O(n) square complexity. And now we'll be talking about the second algorithm, that is BBS. BBS stands for the branch and bound skyline algorithm, which is a highly efficient method that leverages a pre-built R tree. It performs a single intelligent traversal of the R tree to identify all the skyline points in the dataset. Its efficiency comes from its ability to prune entire branches of the R tree that are dominated by a known skyline point. In this slide, we'll be talking about the pruning principle in the BBS algorithm. The BBS algorithm maintains a list of confirmed skyline points during its traversal of R tree structure. For any MBR encountered, it checks if the MBR's most optimal corner is dominated by any known skyline point. If the entire MBR is dominated, the algorithm prunes that node, avoiding checks on all points within that region. And now we'll be coming on to the third algorithm we used, that is BBS with divide and conquer. This strategy first partitions the dataset into two distinct subspaces. For example, based on the median housing cost, it then builds an R tree for each subspaces and runs BBS algorithm. A final merge step is required where the two local skylines are compared against each other to produce the final global skyline.
Moving to task 2, that is performance and result analysis. The three Skylines autumn algorithms were benchmarked on the selected city datasets with total execution time as a primary method. The result clearly showed that the standard branch and bound skyline algorithm were the most performant of the trees. The R-tree-based BBS was significantly faster than the BNL, while the divide and conquer method slower due to overhead. The visualization of the final skyline output showed showed that the skyline query is not a single point, but rather a set of optimal data points. These points represents the best possible trade-off between the two dimensions, that is total cost and per square meter. The overall algorithm performance comparison Across both task 1 and 2, the R-based R algorithm significantly performed compared to the others. This demonstrates that the initial and one-time cost of building a spatial index is worthwhile investment for accelerating queries. The standard branch and bound approaches were more effective than the divide and conquer strategies. The key learnings from the project and key learnings and takeaways from the project is that this project provided a deep and practical understanding of implementing an R trees and associated search algorithms. It also helped us to dive deep into uh, how each search algorithms work and how they are differentiated from each other. It, emer- it, it empirical verified the immense performance benefit of special index over naive brute force method for common special queries. The effectiveness of pruning strategies, which are central of both BAB and DBS, were clearly demonstrated to the results. Conclusion and summary is that all the required algorithms for both nearest neighbor search and scaling up computation were done. The project successfully demonstrated that the R-tree-based branch and bound provides provide a better performance and has more gains. The final reports and source code and outputs were generated fulfilling all the required outlined in the assignment brief. The future eh, the future work and potential enhancement that can be done is where the tree construction could be improved by employing more advanced techniques or linear cost algorithms. The algorithms could be extended to handle higher dimensional data, moving beyond the 2D point used in this project. These are the references that helped us to do our assignment and provided great insight and help us learn more about this topic. Thank you.